Sometimes I think, how do I stop? I forget, you know. So the cup was trying to go straight. The water was trying to go straight. This tray pushed them toward the center, and they pushed back, and they stayed on the tray and didn't come off. So that's how a loop-the-loop and a roller coaster work. All right? Okay. If you have questions when we get to the end, you can ask me questions. All right. With all the here we go. So second topic, musical instruments, in particular a stringed instrument. So a violin, a guitar, and even a piano. So the story starts with how does it make sound? And why, when you play a musical instrument, if you play it quietly, it makes a sound. If you play it loud, it makes the same sound, just louder. It's the same pitch. It sounds the same, it's just louder. That's not... The reason for that is a little bit complicated, so I'll show you. To start talking about how a string works and how it vibrates, I'm going to start simpler with the simplest of oscillating systems. Oscillating meaning it moves back and forth rhythmically. And the system I have in mind is an object on a spring. Bounce, 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 bounce. This is a special kind of oscillating system that cycles. It's special because it takes the same time to complete its trip, whether it bounces a little, that's little, or a lot. This is known as a harmonic oscillator. It has the property that it has a spot it likes to be at, what's known as an equilibrium. This is equilibrium. When the object is there, it can stay still. It doesn't have to be still, but it can remain still there. If I pull it away and let go, it accelerates back toward the equilibrium. It's trying to go to that special spot every time, whether I go above or below. The spring pushes it back to that special equilibrium. And it pushes harder when you're farther away from it. If I go very far away, it pushes very hard. And that relationship, having an equilibrium and having a force pushing back, a push back toward that spot that gets stronger as you go farther away, that creates a harmonic oscillator. And the special feature of a harmonic oscillator is the rhythm is steady and doesn't depend on how big the bounce is. For musical instruments, that means the rhythm doesn't depend on how loud the instrument is. So when you play a stringed instrument, if you play soft or you play loud, you get the same pitch. You don't have to adjust to play loud, to play soft. Same use of the instrument. All right. So this is an animation of a mass on a spring. I turned it horizontally. So there's the object, there's the spring, and it's attached. Just that was my hand before. So it's object, spring. And this is the equilibrium place where the mass can sit there. If you put it there, it can stay there. If you pull it away from there, it experiences a force back, and it oscillates back and forth about that spot. Just the same thing I showed you. If I take 3 of the same exact systems and set them going, this one's moving a little, medium, and this one's moving a lot. They're the same rhythm. So, what would I do to change the rhythm? A couple things I can do. This oscillator has 2 parts to it. It has a moving object with inertia and a spring that says go back to that equilibrium. The more inertia this object has, the harder it is for the spring to turn it around and send it back. So the slower its motion becomes. So now I have 3 different versions, but they have different amounts of inertia, or more technically, mass. This has a little mass, medium mass, big mass. And if I set these guys moving, this one turns around easily. It's very little inertia. Medium, this one's very hard to turn around and bring back. It's so much inertia. The spring fights to turn it around. So this is changing the rhythms, and it will change, when you get to musical instruments, it changes the pitch of the sound. So more inertia slows down the motion and lowers the pitch of the music. This is another change. These are 3 different springs. A very stiff spring, medium spring, a very soft spring. This one is going to have a hard time turning around that mass. This spring will turn around very easily. So the stiff spring moves quickly because it pulls back and forth on the mass. The soft spring takes a long time to turn around. So this is going to be like changing the tension in the strings of a musical instrument. As you adjust how strongly those strings are pulled, you change the rate at which the string can go back and forth. All right. Oh. So I showed you one kind of harmonic oscillator. So this is a harmonic oscillator. It follows, it has that steady rhythm, but there are many others. Just a stick on a table. That's a harmonic oscillator. And it's got a steady rhythm, whether a little movement or a big movement. Same rhythm. I can reduce the inertia by shortening the stick. Okay. Yeah, that's good. All right. So what about a string? Because the music on a string instrument comes from that string there. And it's another harmonic oscillator, but it looks like this. This happens to be a spring, just because I want a very heavy, very flexible string. So think of this as a string. It's vibrating. I'm making it go around in a circle, but that's just a technical detail. And if I use less mass, it goes faster. If I increase the tension, it goes faster. So it's a harmonic oscillator, and if I increase the inertia, it slows down. And if I increase the tension, it speeds up. So I can show you some animations of that also. What I want to show you is, you can barely see it. If you pull it away from it, its equilibrium is a straight line. If you pull it away from equilibrium, it fights to go back. It experiences forces, pushes to go back. So it wants to be straight. So this is the simplest motion of a spring. String. And it's just going back and forth about that straight equilibrium, the shape that it can settle at. And if you make it move a little or a lot, if it moves a little or a lot, it has the same rhythm. It'll come in a second. There we go. There's a little motion, up and down, just a little bit. And here's up and down a lot. Same rhythm. Well, okay. Too short. So, how can you change the rhythm? We'll add more inertia. So, here's a string that's got more inertia. It has more, technically, more mass. Heavier string. And there's a thin string down the bottom. Thin string, medium, heavy. If you pull them the same, so they have the same tension, you pull them equally, they go at different rates. The massive string goes slowly. Too much inertia. It's hard for it to turn around. The very thin string, with very little inertia, turns around easily. And so its rhythm is much faster. If you pull on the strings differently, so this string is pulled 0.5 units. This string is pulled 1 unit, and this string is pulled 2 units. So you pull harder and harder as you go down. They will also go at different paces. The string that is not pulled very taut goes slowly, but the string that is pulled hard goes much faster. So this is all part of setting up a musical instrument and adjusting it so that it plays the right pitches, what you want. The last thing you can do with a string is change its length. If you shorten the string, this is a short string here. If you shorten it, and it resists being pulled away from the straight equilibrium much more. This short string is hard, it's hard to pull away from the center. The long string is much easier to pull away from the center. So they go at different paces. The short string goes fast, the long string goes slow. So, already then, this explains a lot about a musical instrument, a stringed instrument. The low-pitched notes, so the strings that want to play the low pitches, they are massive strings. They're thicker than the rest. That's a low-pitched string. The high-pitched strings are much thinner than the others. Okay? This string can go through the motion faster because it has less inertia. This string has much more trouble going through the motion. The second thing that you can do is when you want to tune the instrument, I'm reducing the tension. It goes through the motion slower. If I increase the tension, it can go through the motion faster. So when you set up the instrument at first, you choose the mass of the strings to be suitable. And when you tune it before playing for people, you adjust the tension of the strings. And when you're playing an actual piece of music, you can adjust the pitch temporarily by shortening the string, by pressing the string against the fingerboard, and as it gets shorter, the pitch goes up. All right? That's almost the story of music, of stringed instruments. There are two other pieces to discuss. One is that a string is more complicated than just a simple harmonic oscillator that just bounces with one motion. The only thing this can do is bounce like that. A string has more ability to it can do funny shapes. And so, in addition to this vibration, it can vibrate in other ways. And I'm going to try to do the other ways. This is always hard when I'm holding the whole thing by hand. You see, it's two halves. This is too hard. It's beginning to form two arcs. Arc, arc. If I can't do it by hand, I can show you with the computer animation what it looks like. This is the simplest way a string can vibrate. In English, it's called the fundamental mode. This is the next most complicated. This is called the second harmonic, and it goes twice as fast. This is the third harmonic. It goes 3 times as fast. And fourth harmonic, 4 times as fast. Strings can vibrate like this, and they do. And not only can they vibrate like that, they can do several of those vibrations at the same time. And that contributes to the sound of the instrument. One of the ways you can tell whether you're listening to a violin or a guitar or a piano is by the mixture of these more complicated vibrations that are taking place in the strings. Okay? One last thing. Strings don't produce much sound. When they vibrate, you can't hear that. Right? Even if I go fast enough, you should be able to hear it. There's almost no sound. Because to create sound, you need to compress the air and uncompress it. You really need to push it together. That's what sound is variations in the air, its density, how tightly it's pushed together, or how it's unpushed. And strings don't do that very well, because the air, as the string vibrates, as it goes up and down, the air just goes around it. It's too thin. So it doesn't really affect the air very much. To affect the air, you need a surface. You need to push on it like this. And the air's inertia keeps it in place as you smush it. You compress it. So thin things don't make sound well. And my example of that is a little music box. So this is just the part of the music box that creates the vibrations. But it's very quiet. You can barely... There's almost no sound. To make sound, I have to make this device shake a surface. So here's a surface. You're hearing sound that's not coming from the music box. It's coming from the surface that's being shaken by the music box. And so all stringed instruments have surfaces with them if they're acoustic. Electric guitars do not. An electric guitar is special. It has vibrating strings and an electromagnetic device that measures those vibrations and uses electronics to make the sound. An acoustic guitar has surfaces, and so does a guitar. So the box of the guitar is crucial to making sound. Okay? And that's true. Pianos, they have a soundboard underneath the strings or behind the strings. Harps, the body of the harp has surfaces to make the sound. Otherwise, you can't hear it. All right? So that's the story of stringed instruments.